Now consider, so I will say another example of regularizer. Suppose, so your data is x comma yi, we have it from pxy. Okay. Now create a new data set as follows. Now let for every xi, okay, for every xi in D, okay, so xi cap is equal to xi plus epsilon, where epsilon is sampled from normal 0 1. You see what I am doing? Take a data point, okay, perturb it. Take a data point, sample from some Gaussian distribution, add, perturb, and now create a new data set. So now D cap is a new data set that will now have xi cap comma yi. So will the distribution of this be same as pxy or different? Will the distribution of this be same as pxy or different? It will be different. Of course it will be different. Why do you think so much? Yeah. So now here is the climb. The climb is, so ERM on D cap is equivalent to please prove this. So empirical risk minimization on D cap is equivalent to regularized ERM on D. And now you can actually, I can actually make this some alpha times I, okay. I just scale my perturbation with I. Now what is the guess? The guess is this alpha is that lambda. Is it directly proportional or inversely proportional? Find it out. This alpha is related to that lambda. A brilliant point here, right? That take your data points, perturb it with some noise and solve ERM. It will have the same effect as regularization. Why do you think it should be the case? So I am saying instead of solving a classification problem on images, add some noise to those images and then solve. It is equivalent to regularizing. Why? Actually, you can see this in multiple ways. Okay, let me hear two of them. Any opinions? Why? That's the point, right? I mean, okay, you take something, add some noise. See, mathematically you can show that the, okay, how do you show this, by the way? What is the way to show this mathematically, algebraically? It's very simple. Write down the ERM on D cap. You get some objective function over optimization over theta. Write down, I mean, you will see that that is equivalent to, that is algebraically equivalent to a regularized ERM on D. That's it. It's very simple. Actually, you can see this. Why should this be equal? Just do that. Okay. So yeah, I will not tell you that. Just try that exercise once. So now intuitively, why should this be the case? It is. Why should that be useful? Exactly, right? Expanding the manifold. So now if you take Gaussian noise and add to it, right? That tiny manifold that you are looking at now will become filled, because Gaussian is the entire ambient space. Okay. Now think, okay, so I think too many things came to my mind, so I just organizing my thoughts. Which one should I present to you first? Now, what happens if I add too much noise to this? Suppose I increase my alpha too much, what will happen to that? So the data will be submerged into noise, no, completely, right? So now if you were to now explain noise, which is a Gaussian distribution, then you will too much bias and you will go to the underfitting regime. So now the reason I just pause for a moment is that I wanted to make this point that the regularization constant lambda that you have controls which point that you are operating on this particular curve. It is the lambda with which you can move around this curve. If you, that's a knob, that's why it's a hyperparameter. If you make your lambda to be very high, then you will push the model into the underfitting regime. If you make it too small, you will be in the overfitting regime. So same thing happens. If you add too much noise, then it will be underfitting. See again, if I were to give the philosophical equivalence of it, right? When would a human being be too biased and underfit? Is when the person is not shown difficulties. It's too easy to learn. सब कुछ आ जाता है ना, somebody feeds you, somebody gives you everything, oh this is world, you get terribly biased. Now how to regularize? Add a noise, right? Make life difficult, okay? It's regularized, so no bias will be reduced. Now make it too difficult, the model will break. That's the point. So that's why that lambda has to be rightly played with, okay, that you are not too biased and not too bogged down with noise and so on. So that's basically, so anyway, so philosophy aside, the point is adding noise to the manifold is equivalent to regularization. In fact, this comes up in multiple ways when we look at generative models. A bit of marketing for my next course, right? So there is this problem called vanishing gradient problems, which comes up with generative models such as adversarial networks. Gradients will simply get saturated, and because of that saturation, you get into problems called mode collapse. I mean, please don't worry if you don't understand whatever I am talking. This is only a marketing technique anyway, right? So what happens there is, one of the ways to solve that is to perturb your data and then build a generative model, because it has the regularization effect, expanding the manifold anyway. We will do all this in a greater mathematical detail in our next course, right, if you happen to come there. Anyway, the point is, remember this, the take home point is perturbation of data has a regularization effect. So why am I saying this? There is one other point that I wanted to make here is, remember what algorithm did we use for optimization numerically? Do you remember the algorithm? Gradient descent, right? So let's write down that. So revisiting gradient descent. So what is gradient descent? We have our r cap theta to be 1 by n, some loss, and please note that all of this treatment is independent of having or not having a y. Everything that we are doing applies to supervised learning, unsupervised learning, generative learning, and everything. Okay, for us, y is one other dimension of data. Remember that, right? Just the distribution changes. Okay, this is our r. So what does gradient descent do? So you have theta t plus 1 is theta t minus some beta times the gradient of the empirical test with respect to theta. So this is what we do in gradient descent, right? This is first order gradient descent, all of us know that. So let us slightly alter this gradient descent. So now what we will do is, so how do we do this? Now define xi belong to dB, where dB is a B length subset of D. So we have data set D, we do a random sampling, a B length random sampling from D, okay, and we define the empirical risk, or we compute the empirical risk for only those B samples, okay. Now what happens is, the altered gradient descent is as follows: theta t plus 1 is some beta times, you compute the gradient over this particular case, okay. Now you understood what we are doing procedurally, right? Procedure wise, instead of computing the gradient on the empirical risk, the true empirical risk, if I can use that, right? Anyway, the entire empirical risk, I do a subsampling of data, okay, and compute the average loss or empirical risk over that subsample, and then do a gradient descent. Now in practice, what is done is that once you do this, how do you know that B, I mean, how do you sample that B length subset is by random sampling, okay. Then you keep that aside and you do another random sampling of that B length subset and keep doing it over the entire data set till the n samples, okay, and then do gradient descent over all those small subsets. And if you run through the entire data set once that way by doing this B subsampling, it's called one epoch of training. Okay, it's called one epoch. So you do a subsampling and you run through the entire data set, it's called one epoch. Anyway, so this is how you do it. Now this is not gradient descent, because we are changing the objective function completely, right? And by the way, this has a name. This is called the stochastic gradient descent. The star of this thing, optimization, SGD it's called, okay, stochastic gradient descent. Now what is stochastic about it? Sampling is stochastic. Here sampling is stochastic. Now how is RB cap or R cap B theta related to R theta? It's a noisy stochastic estimate of that. Now why should one do this? See, of course, one reason to do this is that computing computing the gradient on the entire data set may not be computationally feasible. You need to add those many things. That's not the actual reason. So the actual reason is that this has a regularization effect. Why? Because of the fact that we saw here. Any perturbation of data has a regularization effect. Now any perturbation of gradient also has a regularization effect. Now this is perturbing the gradients, isn't it? If you do a random sampling, right, I mean this, you can actually show this, right, I mean this is probability theory. You take the sample average and you change the n, you do a subsampling of that and compute another sample average, you can show that this is a stochastic estimate of the other, okay. So now SGD is considered, or rather observed, to be empirically superior than the other thing is called batch gradient descent or gradient descent, by the way. SGD is considered to be superior because it has a regularization effect, okay. And by the way, this B is typically referred to as the batch size. You hear this term, no, 32, 64 or whatever, that's called, I mean the number of samples that you take to take the stochastic estimate is what is called as batch size, okay. Right, did I leave anything? Any questions on this? Yes. Come again? That this has a regularization effect? Yes, indeed. So I think, yeah, let me just summarize what we did and then we'll take questions. So we have come to an epochal point in the course, right? So what we did so far is that we formulated the problem of ML as that of, we formulated the problem of ML from two different angles. One was that of estimating the underlying distributions. First of all, we started seeing the data as points in RD, okay. For the empirical risk minimization approach, these are simply points in Euclidean spaces. For the probabilistic approach, these are the points of the range space of a random variable which has an underlying distribution. And the entire problem of machine learning is that if you are given some samples that are sampled from this underlying distribution, you want to estimate the underlying distribution. Okay. So we saw a way to do that. One way to do that is by the procedure, by the idea of divergence minimization, where you define, okay, a divergence between two distributions. One is the true distribution that you are trying to estimate, and the other what we call as the model or hypothesis or the parameterized distributions. You assume a parametric form on the distribution that you are trying to estimate and define a distance measure between the true distribution and the parametric distribution. And you cast the problem of estimating the distribution as that of estimating the parameters of the model or the parameter distribution through minimizing the divergence between the true distribution and the parameter distribution. Okay, this is what we called as the minimal ML estimate, or it also turns out that it is equivalent to maximizing the so called likelihood function, the log of the likelihood function, and we saw a few procedures to do that. So you do it, solve it in two ways. One in the analytical way, which seldom happens, it happens only with primitive distributions, and there is also the empirical or the numerical way of doing it. Either you do it using numerical differentiation, or for the cases of latent variable models, you resort to this iterative algorithm called the expectation maximization algorithm, right? And there is this ERM angle of looking at things, where you say that okay, there are two sets and we are trying to learn a function between these two sets. There is an underlying function that is unknown. We define what is called as a loss function, and we cast the problem of learning the hypothesis as minimizing what is called as the empirical risk, okay, or the expected loss function. And since we do not know the underlying distribution to compute the expectation, we take the empirical estimate of it using the law of large numbers, which we solve ERM. And we also saw that there is a one-to-one equivalence between solving problems using the empirical risk minimization framework and divergence minimization framework, and they are exactly equivalent. And we also saw these classes of algorithms where we make an assumption not only on the hypothesis class or the underlying model, but also on the parameters that we are looking at in terms of distributions, and these are the Bayesian methods, and we saw an example for that which is called the map estimator. And we also saw that distributional estimation can be done in a non-parametric way. Remember Parsons window and nearest neighbor estimates, right? Where you can estimate the distributions, not estimate, evaluate the distribution at a given point, which is what we need to realize some of the hypothesis functions in a non-parametric way. And we also saw that if you are considering a classification problem, then the hypothesis that would minimize the true risk is the one that chooses based on the posterior of the labels, and this is called the Bayes classifier. And one can use distributional estimation techniques to realize a Bayes classifier. Okay, and we also saw from the ERM angle different choices that one can make to the hypothesis functions, and then solve ERM to get the parameters. Specifically, we saw the linear classes of models, which we generalized to the generalized linear models. And we saw a few examples of the linear regression and the logistic regression, right, with a particular kernel function where you change your data, you have a particular function that transforms your data, and then you find the parameters through either the analytical differentiation or through numerical methods. Okay, and we also saw that that when we are trying to solve this problem in a pragmatic setting, we end up having this bias variance dilemma. Okay, and which is actually that the risk that we are trying to minimize, okay, gets decomposed into two different terms, and typically we want both of them to be, or rather we want both of them to be minimized, while typically we can't minimize them simultaneously. So pragmatic approach is to start with a model that has very low bias and high variance, and then push it back. And this procedure where you increase the bias of a model is what is called as regularization, and we saw a few ways to do it, where one is to put an explicit, solve a constraint optimization problem by putting a constraint on the parameter space, or then you perturb the data with some noise, and you change the architectural or the choice that you make on the hypothesis function, and so on. Okay, did I just summarize the half of the course in 5 minutes? I don't know, whenever I do this, I feel like, why did I spend half a semester teaching this? Anyway, so this is how you should look at all ML algorithms, and this treatment, okay, is common across all the ML algorithms that you see. Okay, be it the generative models, be it discriminative models, supervised, unsupervised, and all this. This is what we do. Now, in the rest of the course, we will continue our journey by looking at different choices of the hypothesis function. The next that we will look at is what is called as the kernel methods, okay, of which support vector machine is a member. SVM is not the go-to choice for classifiers or regressors in today's world, albeit it's an elegant formulation. It's an ML course is not complete by looking at SVM. Okay, so when we were students, an ML course would stop with SVMs because that was the state of the art. Now it's the neural network. So we will look at kernel machines and SVMs. I'll quickly do it in a couple of classes. Okay, before coming to the next class, please brush up your optimization fundamentals, specifically the primal dual formulations. Are you people aware of these things called KKT conditions and so on? Please look at them, because we will use that in kernel machines and SVMs. We actually write down the KKTs and so on. So brush that up. After SVMs, we will straight away jump into the neural networks, or this course is called. So we do have neural networks. So we will go to neural networks and spend some time on that. We'll look at this one algorithm called backpropagation, and then we will go to specified architectures such as CNNs, RNNs, and transformers quickly, and finally some unsupervised learning algorithms. Okay, that's how it's going to be. Yeah. So thank you. This ends this current class, and we'll meet in the next class.